This is AP Calculus BC, and in this video, I'm going to talk about trig substitutions. And before I get into this topic, I just want to give you a little bit of background on this. So we are talking about integration techniques in this unit, and trig substitution is actually an integration technique that is not required in the AP curriculum. However, it's something that a few years back I decided I really needed to teach because a lot of you are going to use your credit from the BC exam and you're going to jump straight into a Calculus 3 course in college. If you do that, your instructors are going to have the assumption that you actually have seen trig substitution before. So even though it's not something that'll show up on the AP exam, it's something that I want to make sure that you've seen so that when you see some integrals in multivariable calculus that involve trig substitution, you'll at least have an idea of how you can solve those types of problems, and it'll be something that you're a little bit familiar with. So we're not going to go super in depth on this, but I'm going to give you at least the main idea of trig substitution. Okay, so as far as trig substitution goes, where we have seen integrals that would involve trig substitution really was last semester when we were talking about arc length and surface area. We had a lot of integrals that showed up with specific forms inside of a square root. And they were these forms: square root of a constant squared minus x squared, a square root of x squared plus a constant squared, and square root of x squared minus a constant squared. So for us, they were typically square roots. They're not always going to be square roots, but that's where we're most commonly going to use trig substitutions for the applications that we have. Now, all of this method of trig substitution is not really a new method. We've done substitutions before. It's just that this is a specific type of substitution that's maybe just a slight modification of the U substitution method that we previously looked at. All of these are going to involve the idea of Pythagorean identities, and we're going to use Pythagorean identities to transform an integral from a form that we can't really work with into a form that will allow us to get it in terms of trig functions that we can then typically integrate. Okay, so I'm going to skip to the last page on this just to show you the main idea here. Now, when we do these substitutions, there's really three setups, and I showed you these three setups: square root of a squared minus x squared, square root of a squared plus x squared, and square root of x squared minus a squared. So we have kind of a standard substitution that we're going to do, and I'm going to show you how this works in just a minute, but I want to just show you the substitutions first, primarily because I want you to see how they all use the Pythagorean identities, which you see over here. Those are just your Pythagorean identities written in whatever form is most convenient for the particular substitution that we're going to do. So you can see that when we have the square root of a squared minus x squared, we're going to use x is equal to a sine theta. When we have square root of a squared plus x squared, we're going to use x is a tangent theta. And when we have square root of x squared minus a squared, we're going to do x equals a secant theta. And the reason we're going to do that is because it's going to allow us to take advantage of these three identities, and that's going to allow us to rewrite our integral in a simplified form. Okay, so I wanted to give you that on the front end so that when we start actually working through these problems, you can kind of see what we're getting at and where these substitutions are coming from. Okay, so let's go through a couple of problems here. We're not going to do a ton of these, but we're going to go through a few of them. So we have the integral of the square root of 9 minus x squared divided by x squared dx. Okay, so we have something that's in the form of the square root of a squared minus x squared. So what we're going to do is we're going to use a substitution. We're going to let x be equal to 3 sine theta. And if we do that, that means our dx would be equal to 3 cosine theta d theta. Now, remember when we did a u substitution, we kind of did the same thing, except we would have said u is equal to something, and then we would have gotten a du is equal to something times dx. We're doing a similar type of setup, but this time we're coming up with an expression to plug in for x, as opposed to having like an actual, like, say your u is 9 minus x squared and your du is negative 2x dx. So it's a slight modification of the method we used before. Okay, so when we do that substitution, what happens to this integral is this. We're going to rewrite this as the square root of 9 minus x squared becomes 9 minus 9 sine squared theta. And that is because x is now 3 sine theta. And then the denominator, x squared, is also going to be 9 sine squared theta. Okay, now our dx, remember, is the same as 3 cosine theta d theta. So right now it looks like kind of a mess. It doesn't seem like I've done anything to help my situation. But you'll see that because we chose the substitution that we chose, we're going to be able to actually simplify this down a little bit. Okay, so in the numerator here, 9 minus 9 sine squared theta. I can take the 9 out of the square root, and that would give me a 3. And then we'd be left with the square root of 1 minus sine squared theta. Well, the square root of 1 minus sine squared theta is the same as the square root of cosine squared theta, so this just becomes cosine theta. Okay, so that's kind of the main idea behind it, is trying to get rid of the square root, because the square root is really what was causing me a lot of problems here. And then what we also have, still in the denominator, we have this 9 sine squared theta. And then over here, we still have this 3 cosine theta d theta. Okay, so we're just going to simplify this a little bit and get it into a slightly different form. So you can see we've got 3 times 3, and we've got a 9, so we can cancel that out. And in the end here, we've got a cosine squared theta over a sine squared theta times d theta. Okay, so again, not really something that I can work with very easily, but you can see that this is really starting to simplify down. And in the end here, I can rewrite this as cotangent squared theta d theta. Okay, so once you get to the point that you've got these all simplified out, then it just turns into kind of feeling your way through these things. Sometimes it'll involve a U substitution. Sometimes it's going to involve using some trig identities. So we have to kind of figure out, okay, is there a trig function that has a derivative of cotangent squared? And there's not. But if we use a Pythagorean identity, we can rewrite cotangent squared theta as cosecant squared theta minus 1. And if I've got it written in that form, well, there is a trig function that has a derivative that involves a cosecant squared. The derivative of cotangent is negative cosecant squared. So that means that I can actually take the antiderivatives here. This is going to give me negative cotangent theta minus theta plus c. Okay, so I was able to solve the integral out. Now, the problem that I have is my integral is in the form of a theta, right? My solution is in terms of theta. My original integral was in terms of x. So I want to convert this back to be in terms of x. So what I'm going to do is I'm going to go back to my original substitution that I had here. And remember, I had this x is equal to 3 sine theta. So I'm going to rearrange that, and I'm just going to draw a triangle here. So I can also say that sine of theta is equal to x over 3. And I did that because now I've got it in sort of a more familiar form. Our original substitution said x is 3 sine theta. Okay, so now thinking about what a right triangle would look like with that trig ratio. Let's say this is theta. The opposite side would be x. The hypotenuse would be 3. That means that this side would be the square root of 9 minus x squared. Notice that we've got some of those same expressions that were in the original integral, the square root of 9 minus x squared, that showed up again now when we create this triangle. Okay, so now what I'm going to do is I'm just going to substitute into this. So this means that cotangent, remember, is the same as tangent is opposite over adjacent. So cotangent would be adjacent over opposite. So I have negative square root of 9 minus x squared over x. And all I'm doing is looking at this right triangle over here. I'm looking at this triangle, and I'm using trig ratios to come up with what cotangent is. Okay, now theta, I can go back to this expression. If I wanted to solve for theta, theta would be the same as the inverse sine of x over 3. So that means this would be minus the inverse sine of x over 3. And then I've got my plus c. So in the end, I'm able to integrate that original expression, square root of 9 minus x squared over x squared, even though none of our other methods would work. We're able to rewrite it in terms of trig functions, and then that allows us to solve the integral out. So it's kind of an involved process. Once you've practiced with these a little bit, the substitution part of it is not so much the hard part. Where usually you're going to start to run into issues is after you've done your substitution, then you have to start messing around with the trig ratios and the trig identities and figuring out how exactly am I going to solve this and then simplify it out. So a little bit more complicated process than like a U substitution that we did before, but still the same general premise. Okay, so we're going to look at a couple more of these. So on this next one, we have 1 over x squared times the square root of x squared plus 4. Okay, so looking at our substitutions, you can see that this one is actually going to use this form, the square root of a squared plus x squared. So that means we're going to do x is a tangent theta. Now, you can always kind of remember how these things are going to simplify out, knowing that I need to make a constant squared plus my variable squared simplify into something. That tells me that I've got to use a trig identity that involves a 1 plus something squared. So you can just take your trig identity, your sine squared plus cosine squared is 1, and just start thinking about how can I manipulate this thing so that it will work to do my substitution. So you don't necessarily have to memorize all of these substitutions. You can really just think of it as rearranging the Pythagorean identity into the most convenient form. Okay, so we know what form we're going to use now. And so what I'm going to do here is I'm going to let x be equal to 2 tangent theta. Okay, so in this case, x would be 2 tangent theta. And that means my dx is going to be 2 secant squared theta d theta. Okay, so that's my substitution. All right, so before I do my substitution here, I just want to kind of think about, all right, so again, where that substitution came from was the idea that I know if I can get a secant squared, or excuse me, a 1 plus tangent squared, I can get it into the form of a secant squared. So that's going to allow me to kind of simplify this thing out. Okay, so let's do the substitution here. So this would be the same as the integral of 1 over x squared is going to become 4 tangent squared theta. And then the square root expression, again, I have x squared, so that's 4 tangent squared theta plus 4. And then remember, dx is not just d theta. Dx is actually going to be 2 secant squared theta d theta. Okay, so that's my substitution. So now I've got to simplify this out a little bit. And remember, if I've done this correctly, my square root's going to go away because that's really what I was trying to accomplish here. So in my denominator for this, I'm going to end up with 4 tangent squared theta. So the 4 in the square root could factor out. It would become a 2. And then tangent squared theta plus 1 would be secant squared theta. So then this just becomes 2 secant theta. So my square root is gone, which is what I wanted. I'm still multiplying by that 2 secant squared theta d theta. And now I can simplify a little bit more. And when I simplify a little bit more here, what I'm going to end up with is this. So I've got a 2 here that's going to cancel out with a 4 and a 2. So essentially I'm going to have a 1/4. So I'm just going to put the 1/4 out in front of the integral so I don't have to have it in there, just kind of messing things up. I have a secant squared and a secant that will cancel down into a secant theta. And then in the denominator I have a tangent squared theta. Okay, so you can see how this is now starting to simplify down kind of nicely. Okay, so keep in mind, secant's the same as 1 over cosine. So what I'm going to do here is just think of secant as 1 over cosine theta. And then dividing by tangent squared is the same as multiplying by cosine squared theta over sine squared theta. So this is the simplifying that I'm doing to get from the step that I'm on to my next step. So I've got a 1/4 out in front here, and this whole thing is going to become cosine theta over sine squared theta d theta. Okay, so at this point, I've got to kind of think about how am I going to go about solving this out. Well, in this case, if you look at the denominator, it's a sine. I look at the numerator, I have cosine theta d theta. So I can actually do a u substitution now. So I'm going to do a second substitution on this problem and say u is sine theta. That means my du would be cosine theta d theta. Okay, so that makes this whole integral turn into 1/4 times the integral of 1 over u squared du, which then just gives me negative 1 over 4u plus c. And if I back substitute the u into this, I'm going to get negative 1 over 4 sine theta plus c. Okay, so I'm still not done, but I'm close, right? So the last thing I need to do is I need to get this integral back in terms of x. So remember we had this original substitution that we did here. X is equal to 2 tangent theta. So that means tangent theta would be equal to x over 2. So I'm just going to draw a triangle like we did on the last problem. So I know that this would be related to a ratio in a right triangle. If this was theta, the opposite would be x, the adjacent would be 2. That means that the hypotenuse would be the square root of 4 plus x squared. And now from that, I can get my final solution here. So using that triangle, sine theta would be the same as x over square root of 4 plus x squared. Since it's in the denominator, I'm going to take the reciprocal of that, and I'm going to end up with negative square root of 4 plus x squared all over 4x, and then plus c. Okay, so in the end, this one was not as difficult because when we got to the point here where we had everything written in terms of theta, we were able to actually get our antiderivative pretty easily. There were no trig identities involved. It was just a simple u substitution. But like I said, that step that I have circled, it's really these two steps. When you get to that point, that's always going to be sort of the crux of the problem. If you can figure out what to do when you get to the situation where you've got everything in terms of theta, then it's really all downhill from there. But that's the tough part, is it just turns into an integral with trig functions. A lot of times trig identities, maybe u substitution, but somehow you're going to have to sort of feel your way through that to figure out what you're going to do once you get everything in terms of theta. All right, the last one I want to show you here is a substitution with definite integrals. So when we have definite integrals, just like when we do substitutions with a u substitution, the nice thing is we can transform our limits of integration, and we don't have to do all the back substitution when we have definite integrals. So in this case, notice that we've got 4x squared plus 9. So we essentially have the x squared plus a squared set up. And what I want to do is I'm going to use this scenario. So I'm still using the same substitution that we just did. X is equal to a tangent theta. The difference here is my x, I'm going to sort of do this and make the x a little more complicated, and I'll show you what I mean by that. Okay, so we know we're still using the tangent substitution. So what I'm going to do this time, where I would normally have an x, I have a 4x squared. So I'm going to take the square root of that. That means that 2x would be equal to 3 tangent theta. And that means that x is then equal to 3/2 tangent theta. Okay, so that's the substitution that I'm going to use. I also know that dx is equal to 3/2 secant squared theta d theta. Okay, so there's my substitution that I'm going to use. Now, keep in mind we've got a definite integral, so we've got to deal with these limits of integration. But when I do my substitution here, this whole thing is going to become the integral, and I'm going to deal with the limits of integration here in just a second. But x cubed would be 3/2 cubed is 27 over 8. And then tangent cubed. And then in the denominator, remember what I really want to do is get rid of this square root that I have. 3/2 power means we're going to cube it and then take the square root. So what I have is the 4x squared becomes 2x squared. So that's going to be the 3 tangent theta expression squared. So that's going to give me 9 tangent squared theta plus 9. Remember that's to the 3/2 power. And then my dx is 3/2 secant squared theta d theta. Okay, so what I have right now are x values as limits of integration. And what I want to do is I want to convert those over into theta values. So to convert them over into theta values, we can sort of think about the fact that tangent theta would be equal to 2/3 x. Okay, so whatever my x value is, I can plug that into that expression, and then I can solve for theta. And if I plug 0 into that, tangent of theta would be equal to 0. That means my lower limit is 0. If I plug 3√3 over 2 into that, I'm going to end up with square root of 3. So where is tangent theta equal to square root of 3? It's at a theta value of pi over 3. So all I'm doing is using that expression to modify my limits of integration. So the nice thing is now I've got an integral that's numerically equivalent to the one I started with, so I no longer have to worry about the x's anymore. Okay, so let's do some simplifying here. All right, so this is a little bit tricky because we have this 3/2 power here. But first of all, my limits of integration are set at 0 to pi over 3. For the moment, I'm going to leave this as 27/8 tangent cube theta. And in the denominator, let's think about what would happen here. You could factor out a 9. If you take the square root of 9, you're going to get 3, and then cube that, that's going to give you 27. Okay, then I would also have, once I do that, I'd have a tangent squared plus 1 to the 3/2 power. Well, tangent squared plus 1 is the same as secant squared. Secant squared square rooted gives me secant, and then cube it, so I'm going to get secant cubed. And then remember, we're multiplying by this 3/2 secant squared theta d theta. Okay, so still a little bit messy here. We've got to be really careful with these fractions, but it's still the same general idea as what we did before. Okay, so at this point, we've got a 27 divided by a 27. We've got an 8 multiplied by 3/2, so that's going to give me, let's see, 1/8 multiplied by 3/2, that's going to give me 3/16. So I'm going to factor out the 3/16 that I have. So I've got 3/16 times the integral from 0 to pi over 3. And then let's just simplify the expression that we have. We have a secant squared and a secant cubed. So in the end, we've got tangent cubed theta over secant theta d theta. Okay, so again, this is where we kind of get to the hard part, because now we have to figure out, all right, what are we going to do with what we're left with here? Okay, so tangent cubed theta divided by secant theta. Remember, secant is the same as 1 over cosine, so if I simplify that out, that's the same as 3/16. I'd have the integral from 0 to pi over 3, and this would then become sine cubed theta over cosine squared theta d theta. Okay, so now we're at really the hard part of the problem, because we have to figure out how are we going to deal with this, because we've got a sine cubed, we've got a cosine squared. We can't do a direct kind of substitution right now. We have to start thinking about how we can manipulate this. And like I said before, this is where you're typically going to get stuck. So you've got to think about different ways you can manipulate the expression. And one thing that we can try is in the numerator, we've got a sine cubed. Well, rather than writing it as a sine cubed, I can take a sine squared and make it into a 1 minus cosine squared. And then I would just have a single sine theta remaining. And in the denominator, I've still got a cosine squared theta. And I've got my d theta, right? Well, at this point, I can actually do a u substitution because I could make u cosine theta. My du would be negative sine theta d theta. So I'm going to do a u substitution. So u is sine theta. My du, or excuse me, u is cosine theta. My du would be negative sine theta d theta. Okay, so there's the substitution that I'm going to use. And again, it's not obvious right away that that's how we're going to solve it out, but that's what we're going to use to simplify. So I'm running out of space here, so I'm going to move over here to the right. And when I do that substitution, this whole thing is going to become 3/16, and it's going to be negative because I've got to put a negative in there with that sign. My integral is going to change. My limits of integration are going to change again. I'm not going to deal with that just yet. But my 1 minus cosine squared becomes 1 minus u squared. The cosine squared becomes u squared. And then sine theta, negative sine theta d theta becomes du. And now my lower limit of integration, I want to convert these to u values. Cosine of 0 is 1. Cosine of pi over 3 is 1/2. Okay, so now I've got a really simple integral that I can solve. So you could rewrite this if you wanted to. You can make this 3/16 times the integral from 1/2 to 1. Then I can make this 1 over u squared minus 1 times du. And then obviously we just use the power rule, do some substitution with the numbers in, and we're going to end up with 3 over 32. Okay, so for the most part, the individual steps are not difficult. There's always one part where it's going to get tough. And in this case, it's when we got right in here, right? We got it in terms of theta. We got everything simplified down. And we had to decide what are we going to do that's going to allow us to actually take an antiderivative. So that's always going to be the tough part. So I didn't give you a ton of these problems for homework because obviously there's a lot of steps involved. There's a lot of thought involved. So there's not a lot of repetition here, but the main thing is I want to give you exposure to trig substitution. You will have these questions on your quiz. You will have them on your test. However, these are not things that are going to be on the AP exam. So we'll hit them pretty hard during this unit, and then you really won't see trig substitution much after that. So it's one of those things where you'll get exposed to it, and then hopefully if you're taking multivariable calculus next year, whether it be with me or whether you're taking, calculus 3 in college, when they bring up trig substitution, it'll be something that you're somewhat familiar with.